The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Well, welcome back to the New Quantum Era. We have today a contributor in quantum computing that almost needs no significant introduction. We were lucky enough to score an interview with Scott Aaronson, who's a leading theoretician in this space. Very, very fascinating person with a long list of relevant achievements for the scope of our podcast. He's also the author of, if you haven't seen it yet, the fascinating blog called Shtetl Optimized, a great treasure trove of wisdom. And wit as well. It's a good time.
Yes. Yeah, I really like talking with Scott, Kevin. I think this is a great opportunity to talk to him in depth. I'm always impressed with, he's sort of closely identified with quantum supremacy and the Google Quantum Supremacy experiment, which he helped design. But I think that's, thinking of him as the supremacy guy is selling him very short. He's sort of omnivorously curious. He's, he spans a lot of different areas within not just quantum computing, not just complexity theory, not just computer science, but he's sort of generally curious.
Yeah.
He's generally curious. He's really good at connecting concepts and extremely good at explaining things and digging deeply into things. So very, very excited to have him on the podcast.
Great interview. We got into some depth on numerous topics of, I think, pertinence to quantum computing, but also here and there straight into a little bit of his new work he's doing with OpenAI. Fascinating stuff.
Yeah. All right, here we go. All right, we're joined today by a very special guest, someone who in quantum computing sort of qualifies for the needs no introduction kind of category, I think. We've got Scott Aaronson with us today. He is a theoretical computer scientist, the David J. Bruton Jr. Centennial Professor of Computer Science at UT Austin, and quite well known for his work in computational complexity theory, quantum computing, and very closely associated with the early sort of establishment of the Google supremacy experiment, for example. So we're really excited about the conversation with Scott today and super happy to have him with us. Scott, welcome.
Thanks. It's great to be here.
Thank you.
Great to have you on, man. Yeah.
So, I mean, we always like to start with sort of, how did you get to quantum computing? As a super new field, there's no real established paths, and it feels like everybody has their own little, journey to get into quantum computing. So what was that journey like for you?
I don't know that quantum computing is that new anymore, but in the 90s it was new.
Yes.
And I think as a teenager, I was very into programming, mostly just because I wanted to make my own video games.
Right.
And I quickly realized that while I liked programming, I was awful at software engineering, at sort of making my code work with other people's code, or getting it done by a deadline, or documenting it, or any of that stuff. And I was
who needs all that, right? Yeah.
And I was more drawn to the theoretical side. I mean, I learned what the P versus NP problem was. Had fantasies that everyone must have just been overcomplicating this, and if I just spend a few weeks on it, then maybe with my child's innocence, I'll see further somehow. It's good to be burned, I think, sometime in one's life by that.
Absolutely.
By that experience. And then I at some point I read a popular article about Shor's factoring algorithm, which had just been discovered, a year or two prior. So this would have been, 1995 or so. I would have been 14 or 15. And my first reaction when I read about it was, this sounds like obvious garbage. This sounds like physicists who just do not understand what they are up against. Right? It's like, because the way that popular articles would describe quantum computing then as now was, well, it just somehow kind of magically tries all of the different
all things at once. Yeah.
Right. Shor's algorithm will just try every possible divisor in a different parallel universe. And you're like, that sounds too good to be true. Right. That sounds like, even if it worked on some tiny scale, it's not going to scale up. Right. And, okay, in order to be sure, I had to find out. So what is this quantum mechanics thing after all? Right. And, of course I had read popular science books, or I'd had, high school chemistry where they tell you that, well, the electron is not in one place. It's really just in a smear of probability wave, all over the place until you look, and then it decides where to be, and you think to yourself, like, that that doesn't make any sense. Isn't that just a fancy way of saying that they don't know where the electron is? But then,
with a lot more words,
what was new with quantum computing in the mid 90s was that you could look it up, and at that point there were already web pages explaining it. The web itself was not that old, but there were websites explaining Shor's factoring algorithm, Grover's search algorithm, and they just rather than taking you through sort of years of physics and partial differential equations before you could understand it, they just sort of immediately told you, for this very practical purpose, like, what is the core of quantum mechanics? And it turns out it's that the state of any physical system is a vector. It's a unit vector of complex numbers.
Right.
And, these complex numbers, which are called amplitudes, are very closely related to probabilities. In fact, when you make a measurement, the probability is the squared absolute value of the amplitude of some state. But they're not probabilities, right? You never talk about a negative 30% chance of rain, but the amplitudes can be negative or complex, and that is the source of all the difference, right? And now, it's not just that nature is probabilistic, which that itself would not be the surprising part. God playing dice is not actually as big a deal as
sorry, Albie,
as all the people quoting Einstein think it is, right? Because we would use probability all over the place, even if the world had been classical, right?
Yeah,
the real,
go to Vegas sometime.
But the really surprising part is what we have to do to calculate the probabilities when we're at the atomic scale, and what we have to do is add up these amplitudes, which are these complex numbers. And if something can happen one way with a positive amplitude and a different way with a negative amplitude, then the two contributions can cancel each other out. They can interfere destructively so that the total amplitude is zero and the thing never happens, right? And yet if you blocked off one of the ways that it could have happened, now the amplitude is positive or it's negative, and now the thing can happen. Okay, so probability is not monotone the way you thought it was, right? You can decrease the number of ways for a thing to happen and thereby increase the chance of it happening. Okay, and quantum computing, all it is you just take the theory of computation as it had developed since the 1960s and as I had already learned about, and you combine it with that new twist, with that. So now the idea with a quantum computer is going to always be that you're trying to choreograph a pattern of interference, so that for each wrong answer, each answer you don't want to see, some contributions to its amplitude are positive and others are negative, and they cancel each other out. Whereas for the right answer, the one you do want to see, the contributions to its amplitude reinforce each other. Okay, and this is not obvious how to do that for interesting problems, right? So, computer scientists still have their work cut out for them. Okay, but this is the source of the power, right? And it's a very specialized hammer that nature sort of gives you, and then you sort of, as a computer scientist, you have to figure out what nails can that strange new hammer hit. Right. And that is what Shor did. Right. He exploited very, very special properties of the factoring problem in order to set up a sort of interference experiment that would reveal the answer. Right. And, in some sense, the source of the power is the interference combined with the fact that there is an absolutely enormous number of these amplitudes. Right. If I have a state of 1,000 bits, which can be in quantum superpositions of 0 state and 1 state, so what we call qubits, then the number of amplitudes that I need is 2 to the 1,000 power, right? Which is much more than the number of atoms in the observable universe.
Yeah.
Okay, and in some sense, physicists knew that since Schrodinger, wrote his paper in 1926, right? But it was only with quantum computing that sort of people's faces were rubbed in the full staggeringness of that fact. Right? And finally, in the early 80s, when Feynman and David Deutsch and others started talking about this, the question was finally posed explicitly, like, does nature really work this way or not, right? If it does work this way, then you should be able to exploit it to do computations that would take you an astronomical amount of time to do classically. And if nature does not work this way, then, in a way, that's even more exciting. That's a revolution in physics. So either way, let's find out. And when you put it that way, and when you combined with the fact that in the 90s, like, this field was brand new, and there were just open questions left and right all around. I mean, the case was compelling. It was like, how could you not be interested in it? Right?
Yeah.
And, the main worry at that point was just that I would not be able to do anything new in this area, right? So I had a summer job at Bell Labs about statistical software. It had nothing to do with quantum computing, but my boss was very nice, and he said I can spend a few weeks, reading up on this, and so I learned how it worked. I was very excited to prove some theorems in quantum complexity theory, which I thought would be new, publishable. This would have been in like 97, I guess, when I was 16 or 17. But, it turned out that those theorems were already known. Okay. But it was like, maybe a few years before, I would have been rediscovering math that was like known to Euler or like known in the 1700s. Right. And then I was rediscovering stuff that was known in the 1950s, but then with quantum computing, now I'm rediscovering stuff that was already known, but from like the year before. Right. So I feel like, okay.
So you're catching up. That's right. Step by step.
Closing the gap.
Right, exactly. But then I found out that Love Grover, the discoverer of Grover's algorithm, maybe, the sort of other central quantum algorithm other than Shor's, he had worked at Bell Labs in the same building as me. So I went and talked to him. And, I had some ideas for how to improve Grover's algorithm, which were completely wrong. They just, did not work at all. Okay, but Lav was extremely nice, and he offered me an internship to work with him the following summer.
Oh, cool!
And so I did that, and while I was there, I got to know a student from Berkeley named Ashwin Nayak, who was working with Umesh Vazirani, and at that time, that was kind of the center of quantum computing theory in the world. And so now I was sort of plugged into what was actually happening in this field, and what were the current open questions. And I got the idea that, like, wow, this is really my dream. Like, I wish I could go to Berkeley for grad school and find out whatever these people know, right?
And so you did.
I was an undergrad at Cornell.
Right.
At that time, there was no one at Cornell doing quantum computing.
Right.
But I actually at Cornell, I was working much more in AI. I worked on a RoboCup, the robot soccer team, which was a very important experience, and it convinced me not to become a software engineer.
There is something humbling, I think, about the clips, the video clips of those robot soccer players sort of whiffing the ball and falling over, right?
Face planting hard.
It's impressive, and they're
it's super hard.
It was already cool then, and they're just incomparably more impressive now.
Absolutely.
I watched it recently, right? But again, I realized like I would be off thinking about like, could we formalize this problem about how to move the goalie such that we could prove that it's NP complete, right? And like maybe after a while I'd be like really happy I could finally do that, and like we don't care, we're not doing it.
Exactly.
Maybe not an application guy.
Right. But that summer at Bell Labs, I worked on proving a quantum lower bound, which means proving a limitation of quantum algorithms for a variation of the Grover search problem called called the AND of ORs, okay, which is kind of like I give you a grid and I ask you, is there a black pixel in every column? Let's say, does each column have at least one black pixel? Okay, and you can do this kind of thing by running Grover's algorithm recursively. The question was, could you do better than that? And I tried to solve this problem. I couldn't. And then that fall, Andres Ambayanis, who was another student of Vazirani's at Berkeley, managed to solve that problem by inventing a whole new quantum lower bound method, what we now know as the quantum adversary method. Okay, and so like I felt bad that I couldn't come up with it, but on the other hand, I couldn't have come up with it, right? But I because I spent the whole summer on the problem, I was immediately able to understand it. Right.
Perfect.
And that really solidified that, I wanted to go to Berkeley. And as it happened, I did get admitted to Berkeley for a PhD, but it was the AI people who recruited me there, not the quantum computing people. So I spent a year at Berkeley doing machine learning, actually with Mike Jordan, who's a well-known machine learning guy. And, even then, this was 2000. So this was like a decade before the deep learning revolution started, right? But I could already see that, deep learning is going to, or what was then called neural nets. And statistical machine learning, let's say, was going to have an impact on the world sort of sooner than quantum computing. Let's say, I didn't know how well it was going to work when you just scaled it up, right? Hardly anyone knew that at the time. But I feel like I loved quantum computing more. And the reason was that, in machine learning, then as now, the ultimate test for almost everything is empirical. Right? You don't really understand why things work, right? You try them out, and you see that they do in fact work, right? And you get some, you get some log plot, or some messy data that
or the robot kicks the ball.
Yeah, that's right. It tells you that it's doing well, and again, I felt like if I had any comparative advantage, it was more on the side of explaining why things work. So I sort of secretly, wanted to, sort of join the quantum crowd, or at least combine AI with quantum computing somehow, right? And at that time, in like 2000, 2001, that was just a completely crazy idea, right? Like a decade later, it became a whole industry, right? But at that, like in 2000, I felt like, okay, quantum AI sounds cool, but I just don't know what to say about it that's non-trivial. Right. If I
it was
had
a
just
fun science fiction topic back then, but not.
Right. If I had just waited a decade, what I would have learned was that I didn't have to say anything non-trivial. I could just write papers about it anyway, and there was a community that would eat that up, right?
Just wait for the VC money to foam it up a little bit.
So I didn't see how to combine the things, but then the summer after my first year at Berkeley, I was at Caltech in John Preskel's group, and there was a particular problem in quantum computing theory that Vazirani sort of given out as his favorite. It was called the collision problem. Okay, so it's a variation of the Grover problem. Right? The Grover problem says, you have a black box, mapping inputs to outputs, let's say, and you just want to find an input that is good, like that maps to a one output, right? And for this problem, quantum computers can give you a quadratic speed up. They can solve, if there were n possible inputs, then a quantum computer can find a good one, if there is one, in about square root of n steps compared to n steps that would be needed classically. Right. Okay, but this is also proven to be the best that even a quantum computer can do, at least for that sort of abstract problem. Okay, but now with the collision problem, we imagine a function that maps messages to hashes, so like a cryptographic hash function, something like MD5 or whatever. And now the goal is just to find two messages with the same hash. Okay, yes. So there are many, many pairs of such functions, right? Because the hashes are much shorter than the messages are, but you just have to find any pair. So this is a very fundamental problem in cryptography. And for this problem, it's well known that even classically, so with no quantum computer, there is already a square root speed up to be had over the most naive thing. And that square root speed up comes from what's called the birthday paradox.
Yes,
right? The birthday paradox is the thing where if you put 23 people in a room, there's already a half chance that two of them share a birthday, because what matters is the number of pairs of people. Right. Which grows quadratically with the number of people. And likewise, if I have a function, with n possible outputs, then to find a collision in that function, I have to query about square root of n random inputs, and then probably I'll have found some collision. And now, so we now see two completely different ways to solve this problem in square root of n time, using the birthday paradox or using Grover's algorithm, if we had a quantum computer, right? And in 1997, Broussard, Hoyer, and Tapp had a sort of remarkable paper where they said you could actually combine the two. You can have a Grover-enhanced birthday attack, and that ends up being able to solve that problem in cube root of n steps. Okay.
Oh, wow.
You combine the two square root of n speed ups, you get a cube root of n. Where,
beautiful result. Cool.
It makes a perverse kind of sense, right?
Is that? I mean, do you feel like that's sort of the roots of your own interest in sort of, it's been called sort of dequantizing quantum algorithms, like sort of trying to find classical approaches maybe inspired by the quantum approach, but that are actually...
I think that's been part of the field since the beginning. I think, you could say the dividing line between the serious and non-serious quantum computing research is, are you asking the question of, can you actually beat the best that a classical computer could do at this same task, right? The serious science begins when we ask the comparative question. Right. And, which is as obvious as it sounds. Like, every day I see papers on the archive that are just, do not reach that threshold.
And then you're called upon to debunk them on Shtetl Optimized.
Right. And this is part of how my blog just became prominent. I didn't plan it that way, but it was just that no one else was doing that. It was just that, taking what is obvious to everyone in the quantum computing research community and just saying it out loud to the wider world.
And that was one of the reasons that we had such a primary attraction, having you on the podcast, is that you've just been so great there. I wonder, there's a family of other areas of research in algorithms and quantum computing. You touched on the two major ones, Shores and Grover, but stuff like adiabatic computation, quantum walks. Topological quantum computing, somewhat to the future, measurement-based quantum computation. What's your relative level of faith and optimism that those areas are going to produce, new significant breakthroughs on the order of Grover and Shor?
I would say that many of those already have produced, significant breakthroughs and are, they're a permanent part of our understanding of the subject. But in terms of, giving independent sources of quantum speed up, that really matter in practice. right?
Yes.
That, it's been much harder than many people have hoped to expand the list of applications that we already knew in the 1990s, right?
Right.
And
Yeah.
I think that's the truth of the matter. I think there are many problems that seem amenable to a Grover type speed up. Right, that's like a large fraction of everything in computer science that can get some kind of polynomial speed up, and often it takes a lot of cleverness to figure out how, and to figure out what is the best polynomial speed up. Right, so I was just to complete what I was saying before, like my first big result in quantum computing that sort of got me into the field was to prove that Broussard-Hoyer-Tap algorithm for the collision problem was optimal. Right. So for the collision problem, once again, I proved the first lower bound for the problem, and that was then improved like a month later by a colleague named Yaoyin Shi, and he showed that there's not even a slight improvement over Broussard-Hoyer-Tap. So with enough effort, we've been able to understand for lots and lots of different problems. Collision just being one example. What are the best speed ups that a quantum computer can give you, at least in this sort of black box setting, setting where you imagine that you have a function that how to compute, and you can compute it in superposition, but you don't have access to its internal workings. Okay, so we have many examples of Grover type speed ups in that model. And there are many, there might be many different ways of realizing Grover speedups, including via adiabatic quantum computation, which you mentioned, right? But now the trouble with Grover type speedups is, well, they're not exponential, right? And because of the overhead of building a fault tolerant quantum computer, right? The kind that could truly scale. It's not in practice. It's not that you're comparing n against square root of n, right? It's that you're comparing n against, let's say, square root of n times a million, or times a billion, or times some enormous constant prefactor, right? And so,
because you have to run a bunch of samples through to get appropriate.
And there was a recent paper like treating that as a new revelation, but we've known that for a very long time. And what it means is that to make those quantum speedups really practical, either you need to massively decrease that constant, find much more efficient ways to do error correction, or else n has to be really, really enormous. Right. So then that leaves us with exponential speedups, right? And I think sit from the 90s through to today, we've had two big families of exponential quantum speedups that seem like they could actually matter in practice. The first of those is just for simulating quantum physics itself, right? And this was the original application that Feynman had in mind when he, raised the idea of a quantum computer 40 some years ago. And it seems like so obvious that, what is there even to say about it? But actually, there's a lot to say about it.
Yeah. Well, and it's really exciting to see, things like the neutral atom devices from QEra and Cold Quanta and Pascal. Those are doing things with 256 atoms that would be very, very difficult to do classically already.
Yeah, absolutely. Yeah. I think that is, that is almost certainly going to be the source of the first practical quantum speed ups that we see, for useful problems, whether that's condensed matter physics or, simulating chemical reactions, high energy physics, if we count that as a practical application.
Yeah.
This is, it's sort of what a quantum computer wants to do in its sleep, is to solve problems that themselves are quantum mechanical. It's a minor miracle that you can sometimes coax it into giving a speed up for a purely classical problem, right? But now of course the other big class is breaking our current public key cryptography, which is what Shor's algorithm and its variants do. Now, that's a very important application if you are an intelligence agency or a criminal syndicate.
Yes.
It is not obviously a positive for
And
humanity,
or
to have this ability, right? I mean, what it will mean in practice is that eventually we will all have to migrate to new quantum resistant forms of encryption, and then having put in that huge effort to migrate, if all goes well, we'll then just be right back where we started.
Yeah.
Right.
Yeah.
So,
Yes.
now it's been one of the biggest problems in quantum computing theory for almost 30 years has been, can you expand the list of practical exponential quantum speedups beyond those two families, right? And there have been valiant attempts to do so. So this adiabatic algorithm that you mentioned is basically a sort of you take classical heuristic methods like simulated annealing, right, which are things that are not guaranteed to work. Often they don't work, but in practice, often enough they do, right? They're just sort of local optimization heuristics, and often they work astoundingly well. And now you can take those and you can sort of enhance those via quantum tunneling effects, right? And you can hope that the quantum heuristic algorithm will be, in practice, even better, at least sometimes, than a classical heuristic algorithm. Okay, so that was the idea. When I was around when Ed Farhi and his collaborators introduced this stuff in 1999, right? And
you were at MIT at the time, I think, right?
Yeah, at the time they were super optimistic that this might just solve NP complete problems in polynomial time on a quantum computer, and already then I was very skeptical of that, right? But, they had some data that looked like it, right? But I was at that point, I was just a student, but I was already being this kind of.
Little did you know that being the quantum skeptic would be your brand.
Yeah, exactly. Yeah, right. No, I'm already being this kind of arrogant, complexity theorist saying data schmata, right? It's going to, it's clearly going to become exponential, right? In that particular instance, the arrogant complexity theorists were right, right? That is how it turned out. Okay, but then the question, or rather, there are. It was quickly discovered that one can construct instances of NP-hard optimization problems where even the adiabatic algorithm needs exponential time. Okay, and where the only speed up that it gets over a classical algorithm is basically the Grover speed up. Right. Okay, but then the question became, all right, well that's the worst case. So forget the worst case, right? Couldn't maybe in the typical case, maybe this is a win, and and that's been a discussion that's been going on from the early 2000s all the way till today, right? And unfortunately, I think there's our actual scientific understanding, which sort of very, very slowly advances, right? And Matt Hastings had a breakthrough on the subject just a few years ago, where he showed, for the first time, he could construct an artificial landscape where he could prove that the adiabatic algorithm, reaches a global optimum in polynomial time, and no classical algorithm can do the same, right? Again, in this black box setting, right? But now we still have no idea, will that kind of landscape ever arise in practice?
Right.
Whatever. And for practical optimization problems, people are still squinting at data and arguing about it. Right. And we don't, we may not really know the answer as to what kind of speed ups are possible until we have large quantum computers to test the thing out.
Until we can see the empirical results.
That's the thing with heuristics, right?
Yeah.
They're heuristic, right?
Yeah. Scott, this is such a great deep dive on this algorithm. I thank you for getting into this detail.
Yeah, sure. But in the meantime, this brings us to the saga of D-Wave, right? But
Yes.
what happened starting in 2007 or so was that people learned that, people would get so excited about this adiabatic algorithm, maybe like using tunneling to solve optimization problems faster, and that just fit in so well with the narrative that they wanted to tell, that quantum computers are going to revolutionize machine learning and optimization and financial vehicle routing and financial portfolio planning and all these things. It just fit in so deliciously, with that narrative that people would just not resist the temptation to say, okay, we use the adiabatic algorithm, and therefore, this is practical, and they would just trust that in the business world and in the journalism world, people would not be asking the question, but did you beat a classical computer?
Right.
How did this compare, to, the best classical algorithm, right? And you can't just compare against, classical brute force, right? That's tying the classical computer's hands behind its back. You have to compare to the best classical algorithms, right?
And as you said, that's
yeah.
where the actual discipline scientific work happens.
Exactly. That's where the actual science is, and it's still unsettled, and it's still being argued about, right?
Yeah.
And you can at least there seem to be Grover speedups. Maybe there's more, at least in some artificial scenarios, there's more than the Grover speedup. But will the more actually matter in practice? And I think in 20 some years, we still don't have a satisfying answer.
That's right.
So fascinating. What about the same domain for same line of questioning for quantum walks? Are you an optimist on those, or?
I mean, quantum walks, are often what they just amount to is a way of achieving Grover type speedups for a wider range of problems than you would have expected, right? I mean, this is one way of using quantum walks. So, Andras Ambayanis had a famous example of this in 2003 when he gave an n to the 2/3 quantum algorithm for what's called the element distinctness problem. That's the problem where I give you a list of numbers and I just ask you to find any two that are the same, right?
Yes.
Or alternatively, just tell me if the numbers are all different from one another. Okay, so it's related to the collision problem, but it's harder because there need not be any collisions to find, and if there are, then there might be only one of them, right? So this was one of the first examples of how sometimes there is a Grover type speedup, but you only see it if you do something clever, such as quantum walks. Okay.
I see.
And then now there are also examples where you can get an exponential quantum speedup via a quantum walk. Okay, and the seminal paper showing that was from 2002 by Childs et al. Okay, and they constructed this absolutely bizarre looking graph called the glued trees graph. Right, it's got two complete binary trees, and the leaves of one are connected to the leaves of the other via a random cycle, right? And what they showed is that, okay, if you started, let's say, at the root of one of the trees, and your goal was to find the root of the other tree, right, and you could only do it by making local moves in the graph, then classically this would take you time that's exponential in the depth of these binary trees, basically because you're just going to get to like the middle, the cycle that connects the two trees, and you're just going to get stuck there for like a huge amount of time, just wandering around in this labyrinth, until you happen to find the way to the exit. Okay, but then they showed that a quantum walk will actually just kind of barrel right through in a polynomial amount of time because of quantum tunneling effects, basically.
Yes.
And so this was a beautiful example, and it was actually used in the breakthrough by Matt Hastings and later people that I a few years ago that I mentioned before, where they found that there is also a and ultimately exponential quantum speed up, also via the adiabatic algorithm. Okay, the trouble is like these are all based on extremely artificial graphs, right?
Yes.
So we
Yeah.
don't know, like for taking a quantum walk on a graph that would naturally occur in the wild, whatever that means, right?
Right.
Are
Whatever
there
that means.
are there also exponential speed ups via quantum walk in those kinds of situations? We just I don't think we really know yet.
Interesting.
And so more recently, so since the summer of 2022, you've been working with OpenAI. So you've sort of gone
Yeah.
back to your roots in machine learning and AI.
Yeah.
I'm curious, was that, I mean, does that feel like almost, I mean, it is sort of back to the world of like empirical proofs, right? I mean, it's like, does
Yes.
the model do the thing you want it to do? And you're kind of trying to come in and add some level of explainability or introspection to these models. Is that right?
Well, that's one that was one idea for what I thought I might be able to do. As it turns out, explainability is also an extremely empirical problem, right?
Okay.
And so, unfortunately for me, right? But what happened was that I've since 2007 or so, I've known this community of people who, have felt strongly that the most important issue facing humanity is to prevent an unaligned super intelligent AI from, destroying the world. Right. And that sort of
Yeah.
nothing else matters by comparison to that problem.
Right.
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 And I would just sort of play with this, like I never rejected their premise as impossible, right? But I always felt like, okay, I'm not sure that I really see a research program here, right? It's like supposing that I agreed with you, like what do you want me to do about
Right.
it?
There's sort of a flavor of religiosity in the whole thing,
That's
isn't
right.
there?
It just seems so far ahead that like how do we know if we're making progress on it or not, right?
Yeah.
And I think like people, so and people would kind of be amused and laugh about it. I think that in the last couple of years they're laughing less, right?
Yes. Yes. Yeah.
Or-
Right. It's always challenging to reason about black swan risk, right? And hard to know. Yeah. Right. Yeah.
Exactly.
Right.
Yeah. Maybe a year ago, someone was in the comment section of my blog saying, like, Scott, what is it going to take to get you to stop wasting your life on quantum computing and to work on the one thing that really matters, which is AI alignment, right? And like, how much money would they have to offer you? And I'm like, I don't think it's about money. It's is there an actual meaty question that I can make progress on? And
Yes.
anyway, it turns out that people at OpenAI, some of them read my blog, and
Unsurprising.
I even have a few former students from MIT
Oh, cool.
who went to work at OpenAI, and I
Nice.
knew them. So Jan Leike, who is the head of the safety group at OpenAI, then emailed me and was like, well, we think we do have problems, and are you serious about this? And would you like to spend a year at OpenAI, right? And I was, my first reaction was like, why do you want me, right? I'm a quantum computing person. Like, what do I even know about any of this, right? But I talked to Jan, I talked to Ilya Sutskever, who's the chief scientist of OpenAI, and I found, first of all, they had a lot of extremely interesting things to say, and of course, I had been aware, of what was starting to come out from OpenAI. I had played around with GPT, which even a year ago was already astounding, and it was much less astounding then than it is now, right? And and I felt like, okay, maybe things have changed. Maybe like there are finally artifacts in the world that are powerful enough that AI safety is now a subject where you can get feedback, where like you can see what is working and what is not working, right? Like these things are already going to be they're not going to destroy the world, hopefully, but or turn us all into paper clips or
Right.
whatever. But millions of students are going to use GPT to do their homework for them.
Yeah,
right?
It's true.
People are going to
Nothing
use
stopping
it.
that. Yeah.
Yeah, that's right. People are going to use it to generate propaganda, to
Yes.
generate spam, to impersonate people, to do all kinds of nefarious things. And
to ask someone on TaskRabbit
Yeah.
to pass the "I am not a robot" test.
Yeah, exactly. Right.
I loved how the TaskRabbit person said, "You're not a robot asking me to do this, are you?" It's like,
right.
no.
Right. No, so I mean, they've already shown some limited abilities to deceive humans,
Yes.
in pursuit of a goal, right? And that's interesting, right?
Very.
And I said, okay, so there's clearly going to be a big need to try to prevent these misuses, and even if that is mainly an empirical problem, maybe they're right. Maybe a theorist can help, right?
Mm-hmm.
So and then I said, okay, it sounds interesting, but I'm in Austin, you're in San Francisco. I've got I have to teach. I've got maybe some other year. And then, and they were like, okay, trust us. This is going to be a really big year for AI.
Yeah.
You want to be involved this year, right? And, you can do it remotely from Austin. And,
Nice.
we'll just pay you so you don't have to teach. And, and you can still run your research group, but just also think about our stuff. And I was like, all right,
Very
that sounds
cool.
like a good deal. So,
Compelling offer, no doubt.
that's how I got involved. And, because some people have asked me, the stuff I've been doing at OpenAI has nothing to do with quantum computing.
Right.
Right. It does draw on some of what I know as a theoretical computer science.
Well, and what an interesting contrast, right? You've got very capable, black box that can actually do a bunch of stuff that we don't have a theoretical explanation for, really, versus the work you do in quantum, where it's all pretty much theoretical because there's no real empirical evidence this stuff will ever work.
In quantum computing, only within the last few years have we started to get devices that are sort of even sort of interesting from the standpoint of complexity theory.
Non-trivial,
For most of the field's history, it was there were the experimenters just trying to get 1 or 2 qubits to work. Right. And then there were the theorists off thinking about, if you had billions of qubits, then what could you, plus an interactive prover, a Merlin or whatever, then what could you still not do? Right. The two things the two communities had a very hard time talking to each other. That is
so distant.
That is changing now. Okay.
It is.
The way that I like to put it is that, in order to make progress in science, you typically need at least one of two things, either, math. So, axioms that everyone agrees on and where they can prove theorems from them, or else, experiment or observation. Okay. But there's got to be something external to you that can tell you when you are being a doofus.
Right.
When you're being wrong, when you're wrong, when you have to back up. The best of all is if you have both, right? But at least you should have one of them, right? In quantum computing, until very recently, we didn't have the experiments at anywhere near the scale that we cared about, but at least we had the theory. We knew mathematically, we could write down exactly what a quantum computer would be, right? And ironically, we understood the sort of eventual perfect quantum computer far, far better than we understood the noisy quantum computers of the present, right?
Yeah.
With AI, we don't have a theory that people agree about. That I mean, certainly, we don't have any theorems that would explain the recent successes of deep learning. Right. The best we can say is that we can explain why none of the theorems rule it out.
Right.
Right.
I hear a phrase like emergent behavior, and I think,
Yeah,
oh, you don't know what's
exactly.
going on.
You're pulling a leg right now. Yeah, right.
These things are exploiting regularities of the real world, in the case of GPT, of all the text and the internet that we do not know how to capture in a theorem. Okay. Now with AI safety, I think for a long time people were trying to make progress with neither, experiment nor mathematical theory, and that's just really really hard to do, right? And the failure mode you get, I think people would get into was they would just say, well, assume an arbitrary super intelligence, right, that wants to destroy you, and no matter what idea you have for how to contain it or align it or whatever, well, it won't work because the super intelligence is smarter than you. It's already anticipated what you're going to do, and so nothing works, and so we're doomed, right? And it's like, okay, well, whether that's true or not, it's like you don't make a lot of progress that way,
No.
right? Right.
Yeah.
So, I think now, it's become, now that you have GPT out there in the world, you can, it sort of makes the question much more concrete because you can see how people are misusing it.
Right.
And then you can say, and then you can think about what can we do to prevent that kind of misuse.
Right.
And then those questions might have, theoretical components to
right.
them.
Well, or just having it tackle a problem like you just on Shtetl Optimize, you just posted its results from taking your final exam.
It did,
which it did okay on, actually.
Yeah, so it got GPT-4
good.
got a B on my quantum computing final exam.
Yeah, and then grade grubbed to try to ask for more points.
Well, this was my TA's idea, right?
That was hilarious.
After we gave the exam, we graded it. He said, why don't you now, ask it whether it wants to, request a higher grade, right?
A conversation you're involved with sometimes with students, yeah, right.
Of course, no, and it will grade grub, and in the same kind of way that students will grade grub, right?
With an identical tone, it's just amazing.
About errors that are rather similar to the errors that a student. Right? I mean, look, this is what it's designed to do. It's designed to predict what a person would say or do in this situation.
And I'm just curious, like in something like that, where obviously the field itself is so familiar to you, it's your exam, you've graded students who've taken that exam now for some time.
Yes.
Was there any insight in having GPT tackle was there surprising things it got right or wrong? Did it give you some insight into how maybe there can be a theory of mind for GPT-4?
Well, okay. So I think, we are just at the dawn of the field of robo-psychology. That Isaac Asimov was writing about 80 years ago.
That's right.
The three laws,
right?
Yeah.
This is finally an empirical subject, and there could be hundreds of thousands of papers written just to explore.
Thank God, new jobs for humans.
Yeah, exactly. I have so many friends in AI who are just moping around these days, like lamenting that there's nothing for them to do anymore because all of their special purpose systems are just beaten by GPT, which is this big inscrutable black box, and which they can neither understand nor can they compete with it on scale. And I'm like, okay, but really, just like reconceptualize this. Like, you can now be the first robo-psychologist.
That's right.
Right? And there's just so much to do. There's so much low-hanging fruit.
Oh my God.
So much to do.
And so I mean, I think what surprised me the most about GPT taking my final exam is that unlike students, it did much better on conceptual questions than on calculation questions. Okay,
that's interesting.
So, a calculation question, usually it would set up the calculation in something like the right way, but then it would botch the execution.
Right.
Which of course, students do also, right? But, it would, GPT has no idea how to check its work.
Right.
So, you can sort of make it do, like people have learned all kinds of hacks for sort of, forcing it to check its work and so forth. But in order to make things fair, I didn't use those hacks, right? I just gave it the problems and told them to solve them. And you have to remember that GPT is generating one token at a time, right? Yeah. And it doesn't have any internal state, beyond those tokens that it's generating. Okay, which means that if it starts generating a wrong answer, it just wants to continue.
It just keeps going.
Right. It doesn't want to back up, right? And
it does so with dead calm confidence. It just sounds so perfectly on target. But it's just making stuff up.
Exactly.
That's about the most human thing about it. Actually, is that total assurance that I'm 100% correct.
Right. But if you look at the exam on my blog, you'll see that there are some tricky, there are some conceptual questions that students had a lot of trouble with, that it really just blows out of the water, right? And so much that that I wonder how, was there something in its training data that was, it wouldn't have been exactly that question.
No,
this exam was not on the internet.
I'm assuming it hoovered up all the archive, though. I mean,
that's right. But sure. But it would have hoovered up a bunch of other people's quantum computing exams, and and the trouble is we don't really have explainability tools right now.
Right.
We can ask GPT what in your training data caused you to say that.
Right.
Now, that's something that some people are thinking about. That would be incredibly useful to have.
So useful.
Right.
Well, and it also begs the question sort of about there are domains of knowledge, anything having to do with math, for example, that you can validate the answer, and that's clearly, and there's already a plugin for Alpha, Wolfram Alpha.
Alpha, yes,
that's obviously coming. But the question to me is so the law, anything humanities related, what kind of validation are we going to be able to build? Is there any kind of obviously there's the explainability, but then there's the answer validation.
Well, there's always just humans upvoting or downvoting.
That's true.
GPT's output.
Sure. That's kind of how we decide what's correct anyway.
And of course that is already being done on a very large scale, right? Before the latest GPTs are released to the public, they undergo months and months of this RLHF. Reinforcement learning with human feedback, which is basically, hundreds of contract workers who are, looking at, hundreds of thousands of GPT outputs and giving it little electric shocks when it says something that's offensive or that's misinformation or that's not the kind of thing that people want, right? So
kind of Pavlov's large language model.
Exactly. So it is being RLHF'd, right? And and we can do more of that, and people really disagree. I mean, some people think, that this kind of thing is going to be how we're going to solve AI alignment, right? Because it's it is hopeless to try to write down human morality as a list of rules, right? Asimov tried it with his
the 5 rules,
robotics,
Five
right?
laws,
But if you read his stories, they're all about how that doesn't work.
That's right.
So maybe the best we can do is just treat being moral as yet another machine learning problem, right?
Yeah.
Here are a million examples from all the world's literature and stories and Saturday morning cartoons of here's what a good guy looks like and here's what a bad guy looks like, right? Now generalize from that. Other people are worried that all of this is just too superficial, and that you're really just teaching the AI to appear to be moral, right, or to give you the kind of answers that you wanted to hear, and and that whole time it could be secretly working against your interests, right? So. So that's a debate that people have, I have not. Let's be clear. In this 1 year of sort of spending part of my time working at OpenAI, I have not solved these problems. I mean, I feel like the problem of AI alignment, contains 3,000 years of human moral philosophy as a special.
So you're saying you'll need a little more time.
Yeah, maybe one more year,
Yeah. So circling back.
I've picked off little tiny pieces where I feel like I could say something, right? So the best known thing that I've worked on this year was a tool for watermarking the outputs of GPT.
Yes.
To make it easier to distinguish human written text from GPT written text. And so there were some interesting theoretical problems there. The thing that I think most surprised people is that by using a pseudo-random function, you can watermark the output of a large language model in a way that does not degrade the quality of the output at all. Okay, in a way
that's really impressive. So do you really feel for our listeners that there's room for optimism, that educators could have a decent tool to hunt down this kind of plagiarism?
Yeah. So there is some room for optimism. I mean, the bad news is that no matter what watermarking scheme I or anyone else comes up with, probably a student with a little bit of cleverness can figure out a workaround. Right.
Yes.
They can, I mean, even just, you ask GPT to write your term paper, but in French, and then you put it into Google Translate. Right. And then it removes the watermark. Right. So
you just gave away the secret, Scott.
Yeah. Well, I mean, that one is obvious enough. People are going to find it anyway. Right. But so what you need, seems to be, to watermark on a more conceptual level, right? And or you could say, look, we're just going to use watermarking as sort of one component. What we can do is we can push the rate of false positives, almost all the way to zero. So we can say, if the watermark is there, then the student cheated. Right?
Yes.
So and that might be enough to catch a large percentage of cheaters in practice. But I think that ultimately there will be some cat and mouse game to stay ahead of people misusing these tools. Just like with Google against all the people doing search engine optimization.
Yeah. Are you planning to change your exam at all for next year?
Well, it'll be an in-class exam. So
okay, yeah.
But I mean, in some cat and mouse games, there's really not much to do except just try to be a better cat.
Yeah, just keep playing, right?
Yeah, exactly. So
circling back to quantum, so we can finish on the main topic of this podcast. So I'm just curious, there's a couple of vendors, IBM, I think Atom, a few others that are sort of promising like on the order of 1,000 gate-based qubits in the next year or so, that, presuming they have good enough, gate fidelities, 2 qubit error rates that are acceptable. What, is there anything sort of that you can think of that you're excited about seeing implemented on like 1,000 gate-based qubits with a decent amount of error mitigation? Let's not call it fault tolerance yet, but less noisy NISQI machines.
I wish I had a better answer for you. I mean, we are, the fear in quantum computing is that we are entering a bit of a NISQ desert. Right, we're entering, a region where, eventually,
it's going to be great.
There's an oasis on the other side, which is fault tolerance, right? Right. Once you get all the way to fault tolerant quantum computing, then you can scale up to as many qubits as you want. You can run Shor's algorithm, right? But we've struggled to come up with compelling applications for a NISQ quantum computer, or at least ones that we're confident are going to work and are going to beat a classical computer, right? There are certainly things that you can try and that are worth trying. People will continue to try these optimization and machine learning things. They'll continue to do quantum simulations. And I think, there is some chance that even before we get fault-tolerant quantum computers, that we could start to see, the first useful simulations in material science and quantum chemistry and things like that, right? And then this would be analogous to, let's say, the era in classical computing when you had, analog devices, vacuum tubes, electromechanical relays, before the transistor was invented.
Yeah.
Right. Basically, right. Yes. And so you could have an era like that. I am personally interested in designing better quantum supremacy experiments. Right. I mean, maybe the most impactful thing I've been able to do in my career so far, right, was to, come up with boson sampling and, with, these ideas that helped lead to the quantum supremacy experiment that Google did in 2019, and then that since then has been done by USDC in China and by Xanadu. But these experiments, they've given us new information. I think they've put the ball, clearly into the skeptic's court to sort of, like if quantum computing will not scale, explain these experiments. And, Gil Kalai, famous quantum computing skeptic, has been trying to do that for the last few years. I don't think he succeeded. Right.
No.
But having said that, the trouble is, because, these are only being done with 50 or 60 qubits. Right, which is all that you can do if you still want to verify the answer with a classical computer. And because the devices are noisy, there are classical algorithms to spoof these quantum supremacy experiments that are pretty good. Right, they don't quite match the quantum computer, but they come, depending on how you measure, they come within a couple of orders of magnitude of matching it. Like, let's say, as measured by how much electricity do you need to spend to solve this problem, right? And the quantum computer is, needs a dilution refrigerator to run, which is, pretty energy intensive. The classical, computer, well, you need a lot of cores. And, maybe it ends up being 100 times more than the dilution fridge. That is not as clear of a separation as we'd like. And in particular, it might take only one or two more improvements in classical algorithms before, the quantum supremacy that we have would just go away entirely. Okay.
Right.
So I think that there is a strong need to do better quantum supremacy experiments, and I have some ideas about it, that I want to pursue further. I think the ideal would be to figure out what can we do with a near-term, non-error corrected device that beats a classical computer, and where a classical computer can efficiently recognize a correct answer, right? And we just don't know how to do that yet. This is a problem for us, for the theorists, to figure out how to do that. I have some ideas. I think the kinds of quantum circuits that we need seem to exist. We have some numerical evidence that they are out there. It's just that we don't know how to systematically find them. Okay.
I thought we heard on a previous podcast, I think it was an interview with Dorit, that she was talking about time complexity. Yeah, right. Yeah. Sorry for the pronunciation. About log depth circuits on NISC era machines as a specific class where there could be actually a fruitful set of targets for that exact.
That's right. So there's a little bit different from what I'm talking about. There's a discussion of like, could these quantum supremacy experiments based on random circuit sampling, could they themselves already give you a scalable advantage, right? And so, I think with the existing experiments, like, we never presupposed that they did, right? I mean, my supposition from the beginning has been, if you want to scale, ultimately you're going to need error correction, right? Yeah. And we are only targeting the sort of, near-term regime of, let's say, 50 or 100 or 200 qubits, where where you can hope to eke out an advantage, which is clear, but which is not scalable. right?
Right.
And but now you could get a little bit greedier than that, and you could say, well, but why shouldn't it be scalable, right? And that there's been theoretical progress, including by Dorit herself and Vazirani and others, that has now mostly ruled out the possibility that you can get a scalable quantum speed up via these sorts of experiments without error correction. Except, and there was one case where we thought maybe like using logarithmic depth quantum circuits, and they had a new result from just this year that ruled that.
Yes.
Okay, but I think there's still one other loophole, which is like constant depth, non-spatially local, random quantum circuits. Okay. Where there might be a speed up there.
Interesting.
But I wouldn't personally bet on it. I would just say we might get lucky.
And do you think, because you want it to be verifiable with classical systems, that limits the number of qubits you can run on to like about 50 or so?
With the ideas that we currently have.
Yeah. Oh, I see. Yeah.
Yeah. I mean, we know with Shor, or you could say, or without error correction. I mean, ultimately, Shor's algorithm, right? You can verify that these are the prime factors of your number,
right.
However big it is, but we just don't know how to do that yet.
Yeah. Right. Yeah. Okay. All right. Interesting. Cool. Well, I mean, right. I'm mindful of our time. Any last topics you wanted to touch on, or that was a good.
I think we're good.
Such a good time, Professor Aaronson. Thank you so much.
Yeah, really, really true.
Thanks for having me.
Very much appreciate it. Well, wasn't that fun?
Wow, man. That's amazing.
I really enjoyed that. It was a great conversation.
Great guy.
I really appreciated how he turned a simple ask of like, how did you get into quantum into sort of a giant overview of the not just his history of coming into quantum computing, but almost an entire overview of the intellectual history of quantum computing and algorithms themselves, which I thought was really, really fascinating.
Yeah, ringside seat on that one. Pretty cool, no doubt. I also really liked, for any student of this topic, there's just an intimidatingly huge array of categories of possible subjects of studies when it comes to QC algorithms. I mean, it's kind of daunting, but I mean, I think his framework around focusing on underlining the core importance of Shor's algorithm and the Grover's algorithm, and then he's touching on these other categories of adiabatic computing and quantum random walks, and pointing out that there's some advances there, but there's still a lot of room left for really definitive results in those categories to show some kind of advantage. But I got from him that he has a distinct sense that there's at least some level of stagnation on the discovery of new algorithms. Yeah.
Well, and I think, he, in the section where we dove into the large language models, he sort of drew out, the differences between what ingredients exist in quantum computing and what ingredients exist in large language models, which in terms of progress. And I thought that was really interesting.
That was funny. That sort of notion that you have at least one of two things to discover whether or not you're being a doofus, right? In a science, right? Is either significant experimental evidence or some decent theoretical base and some mathematics to attach to it. If you don't have either one of those, you have no idea. High doofus risk. And then he's sort of putting it in QC. I mean, there's now emerging significant quantum volume that gives really experimental evidence that is making a difference out there. And of course, the theory is super well developed. And in LLM, there's just now with ChatGPT and these new LLMs, there's more and more experimental evidence, and wow, the theory slate looks a little bit blank.
Yeah, I mean, it's startling, I think, that he's spent a year with OpenAI and is finding the large language model sort of resistant to theoretical explanation. I think that's it doesn't bode well. Scott Aaronson's having a hard time explaining
Exactly,
them.
right. It's like, you've got a hard problem when
he's only started, but yeah, it's a hard problem. And I thought it was fascinating, sort of his perspective on how experimental results are starting to catch up with theory and quantum computing. But he made that reference to being a little worried about us entering sort of a quantum desert, which is a new term for us. We've heard quantum winter in the past, but I think, the way I understood it, quantum winter in my mind, of course, is more sort of commercial interest, private sector investment. It's sort of what happened with AI when the industry felt like there wasn't enough progress being made, and sort of capital was withdrawn, resources were withdrawn, and the crops were all dead, and it was sort of make it through the winter with whatever sad little potatoes you can muster from the root cellar. I think what he meant by quantum desert was more that we may not have a ton more productive results on NISQ era machines, and that maybe we're really going to have to buckle down and for the long haul and wait for fault tolerant machines to actually drive more innovation, more progress on the to bolster the theoretical work to date.
That NISQ desert could go on for some time, and that he does stand out as different from other scholars of the space who seem to have at least more optimism in the NISQ era. I guess time will tell. Really, it's an interesting debate, though. These are high level minds operating at an intense level and high stakes stuff. So pretty cool.
I will say, now that I think about it, he also said, that machines that are realizing the promise that Feynman recognized in 1981, and that keynote at Endicott has of, if you want to simulate nature, you need a quantum device to do the simulation. That those are starting to show results right now. The neutral atom devices, in particular, 256 atoms, is very doing a time evolution of a many body problem is a very difficult thing to do classically.
Yeah.
So
yes.
And I think he did say he was optimistic in the near term around simulations in particular. So I think when he's thinking quantum desert, he may be thinking more in terms of
NISQ era machines for optimization problems.
And the more like gate-based, logical, algorithmic rather than simulation. So that's an interesting topic we should dig deeper into that with future episodes. So.
No doubt. Well, it's a great time. I really appreciate being able to show up.
As always.
Yeah.
Yeah. All right. Thanks, Kevin.
All right, great. Thank you, man. Take care.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.